Exercise 12 here is the last exercise in this series on using the SVD for data compression and low rank representation. So here the question is, why did I choose 80 components and not 70 or 103 or 81 or any other number? You did see in the previous few exercises that 4 components is clearly not sufficient, but that doesn't explain why 80 is the right number. The answer is it was totally arbitrary. Oh, not totally. I mean, when I was writing this exercise, I was playing around with different numbers and I just picked 80. So it was kind of arbitrary. And here, what we are going to do is see whether it's possible to come up with some kind of a principled method for determining an appropriate value of this K parameter. So in a for loop, over reconstruction rank, so low rank images between 1 and the total number of non-zero singular values, which corresponds to the smaller of the number of the number of rows or columns in this image matrix, which is 430. So inside this for loop, create a low rank approximation that is exactly what you did in the previous exercise. And now you just want to compute the Frobenius distance between the original and the rank K approximation. So that is basically quantifying this information in here. So compute the Frobenius distance between this matrix and store that. That's going to give you a single number. It's actually the square root of the sum of all of the elements in this matrix here, this errors matrix. And then, run through that for a range of ranks and then make a plot of that. So here you see the error. So obviously smaller numbers are better. It means better image reconstruction accuracy. And here we have the rank of the low rank reconstruction. Now, obviously it's going to be 0 when the rank is 430 because that's just the SVD of the matrix. So that's a full reconstruction, full rank reconstruction. Okay. But, what you would want to see here is something like a precipitous drop in the beginning and then like an L-shaped pattern. So, something that would come down and maybe it would come down to like 50. I'm just making this number up, right? But let's imagine this came down to 50 really fast. And then at around 50 components, it just kind of flattened out like this and went down very slowly. If you found a pattern like that, then basically at that bend, that sharp bend, that would tell you what is the right number of components to include in this low rank reconstruction. But we don't actually find that. It's a pretty beautifully smooth function here. So this tells us that basically every additional rank gives us a little bit more information. And there is a little bit of an exception here at the beginning. But you already saw it from a couple of exercises ago that this is just not workable. You can't use such a low rank for this particular image. So once you've worked through all the code for the previous several exercises, the code for this exercise is not that difficult. A lot of it is copying and pasting. There is obviously some new stuff here. I have a range for defining the different ranks. And then in the loop. So this is the for loop where we loop over the reconstruction rank. You've seen this code before. Let's see here. You have seen this code before. This is the error image. And then, we just sum over all the pixel values and take the square root. That gives us our quantification of the reconstruction accuracy. Okay. And then, I'm just plotting this line here. Now I have a line of code that is plotted out. Sometimes it happens that when you see a kind of smooth function like this and you're looking for a bend or an elbow, and you don't really see one, in some cases, it can be more helpful to compute the derivative here. So that's what I have here. This is numpy.diff. This is basically it's just the difference between each successive element. So the difference between this point and this difference between this value and this value, it is the discrete version of the derivative. So now I'm going to basically just swap which of these lines is commented. And so we can plot this. Now, in this particular case, we don't really get a whole lot of new insight. Again, what you'd want to see is something that comes up fast and then really tapers off very quickly. Now, in this case, it does give us a range, right? The interpretation is you don't want to cut off the number of components here because each component is still giving you a large amount of information, a large increase in information compared to the previous number of components. But there isn't really, it's somewhere around here. Like here, we keep adding more and more components, but we're not getting a much higher accuracy. But when you look at this plot, there isn't a clear number that you would point to as being, the right number. Nonetheless, it's useful to know about this and to explore. It's often helpful to look at the derivative of a function because it's more sensitive than just looking at the function itself for certain kinds of functions. Anyway, I hope you enjoyed this series of exercises on using the SVD for image reconstruction. In the next several exercises, we will explore a similar concept, so using the SVD, but now for image denoising to make a noisy, corrupted image be clearer and easier to look at.